Hi everyone, I'm Yumin Zhang from Harbin Engineering University. Today I will talk about our study, trajectory data collection with local differential privacy. This work is done together with co-authors from Harbin Engineering University and the Hong Kong Polytechnic University. This presentation consists of 4 parts, including problem, statement, and previous work, goals and motivation, solution, and experiments. The first part is problem and previous work. Trajectory data collection is a common task with numerous applications in our daily lives. Analyzing trajectory data enables service providers to enhance their services, leading to benefits for users. For instance, taxi companies can assist drivers in deciding where to wait for passengers by analyzing passenger trajectory data. In the context of trajectory data collection, each user retains their own trajectory locally. They then upload their trajectories to the data collector, which analyzes the data and provides results to the service provider based on various queries. In the absence of proper privacy protection, the direct collection of sensitive trajectory data would give rise to serious privacy concerns. One can apply differential privacy, which is considered the gold standard of privacy protection, to the algorithm used for trajectory data collection. However, differential privacy requires users to upload their raw data to a trusted server and then perturb the data. Such requirements may not always be feasible in practical settings. In contrast to differential privacy, local differential privacy enables users to locally perturb their data and then sanitize the data to the server, removing the dependence on a trusted server. This makes local differential privacy more suitable for the task of trajectory data collection. Here is an example of KR that satisfies LDP. One query is, which fruit do you like, apple, banana, or grape? Seeing that the true answer is apple and the output domain includes 3 items, apple, banana, and grape, the KR randomizer will answer the true answer with higher probability based on K and epsilon and then report it. This provides plausible deniability where the attacker cannot confidently infer whether the reported answer is the real one. The level of plausible deniability is controlled by the privacy budget, denoted as epsilon. A smaller epsilon indicates stricter privacy protection, but may result in poorer utility of the data and vice versa. To apply LDP, users must add noise to their trajectories locally. Satisfying LDP ensures that attackers cannot confidently infer whether a particular user has visited any location in the perturbed trajectory. However, according to the definition of LDP, when perturbing a location in a trajectory, any location is potentially being the output, which may heavily impact the utility of the data. To achieve better detectability, many existing approaches employ relaxed versions of LDP. The only approach that satisfies epsilon LDP is the n-gram mechanism, which incorporates additional external knowledge such as business hours and category information to enhance utility. However, these relaxed versions cannot provide the strict privacy guarantee of epsilon LDP, and obtaining such information may not be readily available in practice and is often not regularly updated. Now I will demonstrate our goals and motivation. In this paper, our objective is to introduce a more practical trajectory perturbation mechanism that satisfies epsilon LDP while relying solely on the essential location set of trajectories. The key observation is that a user's trajectory consists of a time-ordered sequence of locations determined by the user's intentions. For instance, consider a student who is currently at home and wishes to buy a cup of coffee before going to school. The student will search for a cafe, determine the direction between the cafe and their current location, and make their way there. This process is repeated for each target location in the trajectory. The direction information serves as the connection between each pair of adjacent locations in the trajectory. This observation motivates us to explore whether we can leverage such information to enhance the utility of the trajectory perturbation mechanism while still satisfying LDP. Furthermore, according to the first law of geography, the spatial region covered by a trajectory is generally smaller compared to the entire map area. The distribution of region sizes in human mobility trajectories can also be approximated by a power law distribution. Building on this, another key idea arises. Can we apply a method and LDP to confine the spatial region of a trajectory? By doing so, we can limit the number of candidate locations and consequently enhance the utility of the data. Now I will introduce our solution. This is an overview of our solution, which consists of 6 steps. For each trajectory held by a user, we first duplicate the trajectory, creating 2 copies in order to utilize the direction information between neighboring locations in the trajectory. We adaptively restrict different trajectory regions of 2 copied trajectories separately. We then alternately select locations from each trajectory as pivots and independently perturb them. We identify the preceding and the following adjacent locations of the target location in the trajectory as its pivots. A pivot of the target location is treated as the origin, allowing us to determine the direction between itself and the target location. The next step involves perturbing the direction between each pair of neighboring locations in the trajectory. We then perturb the remaining locations considering these direction constraints. Finally, we find the optimal result based on the 2 perturbed trajectories. We illustrate our approach with an example in this figure. Let's consider a trajectory from P1 to P5. Before restricting its region, we first calculate the average location of these locations. This average location is denoted as alpha, and for convenience, we map it to the closest proper location, P alpha prime. To obtain the perturbed trajectory center, P alpha prime hat, we apply the exponential mechanism using a quality function that is inversely proportional to geographic distance. This quality function allows us to find an output location that is as close to the input location as possible. Next, we calculate and perturb the farthest distance between this noisy trajectory center and the locations in the trajectory as the trajectory radius. In our example, this distance is represented by the purple arrow, while the red arrow indicates the noisy distance. We also propose a method to calibrate this noisy distance to avoid a large or too small value. This calibration effect will be reduced with increasing epsilon. By taking this calibrated distance as the radius and P alpha prime hat as the origin, we define a circular area as the trajectory region. This means that the locations within this circular area will be considered as candidate locations for the trajectory. In other words, the perturbation domain of the locations within this trajectory depends on this circular area. After restricting the trajectory region, we further explain how to perturb the copied trajectories. The basic idea is to utilize the directions between neighboring locations and the target location in a trajectory to narrow down the perturbation domain of this target location. In this paper, we refer to these neighboring locations as pivot locations of the target location. However, we have to apply independent perturbation to these pivots in order to satisfy LDP. For example, in this figure, we select P2 and P4 alternatively and perturb them to obtain 2 pink pivots via exponential mechanism. Once we obtain the pivots, we can prepare for the direction perturbation. We first choose a proper direction granularity G and then discretize the direction and perturb it by KRR. For G, we propose a guideline that compares the average direction preserving success probability across different radian intervals of candidate granularities and a given epsilon value. This probability calculates the probabilities of preserving the correct radian intervals and the different G values when perturbed by KRR with a given epsilon value. For example, in this figure, When we have a candidate set of granularities, we calculate the average weighted probability. The weight is the proportion of the pink interval that covers each sector, and the essential probability is the probability of each sector being output by KRR given a fixed epsilon. We will choose the granularity that achieves the best score. Then we can discretize the direction based on chosen granularity and perturb it by KRR. For example, when the granularity is psi to 6, KR is used to obtain the perturbed discretized directions between the neighboring pivot locations and P3. We use the green arrows to denote the noisy discretized directions. Now we get the noisy discretized directions and two pivots of P3. At first, we need to determine the perturbation domain of P3, which is the first type of pivot perturbation. If the intersection of the locations located within the area of the intersection of these two noisy discretized directions is not empty, we choose this site as the perturbation domain of P3. Otherwise, the perturbation domain of P3 is set to the entire perturbation domain of this trajectory that we determined before. Then we apply exponential mechanism to obtain its noisy version, P3 prime height, in green. For P1 or P5, we will only use one side direction to limit the perturbation domain of P1 or P5, as they both only have one neighboring point in the trajectory. We applied a similar procedure to the other duplicated trajectory by setting the pivot locations to P1, P3, and P5. Namely, we independently perturb P1, P3, and P5 under the new noisy perturbation domain of the other duplicated trajectory in order to obtain the new noisy P2 star hat and P4 star hat that incorporate neighboring information. Therefore, we obtain two perturbed trajectories with different trajectory constraints and directional information. We obtain two types of noisy locations in perturbed trajectories for each location in the original trajectory. The first one perturbed only by distance, and the other perturbed under the neighboring direction constraint. Finally, we merged these two perturbed trajectories using an argmin operation to find the optimal trajectory as the output to be uploaded to the server. We evaluate our solution with baselines to show its effectiveness. We use two measures, NE and PRQ. The first one is the normalized distance between each location of perturbed trajectory and the corresponding location of the original trajectory. The second one evaluates whether each location of the perturbed trajectory is within the delta kilometers range of the corresponding true location. We have three baselines: naive exponential mechanism, n-gram without external knowledge, and CGM, a state-of-the-art mechanism for streaming data collection and epsilon delta LDP. So in terms of NE, we can observe that our solutions outperform baselines, which demonstrates both direction constraint and the trajectory region restriction can effectively enhance the utility. For PRQ, our solutions also outperform baselines. We can observe that trajectory region restriction can enhance the utility significantly, even when privacy budget is relatively small. TP can obtain better performance as privacy budget grows, because a larger privacy budget enables the direction constraint to reduce the perturbation domain more precisely, ultimately benefiting the utility of TP. Conclusion: in this paper, we explore trajectory data collection problem in a local setting. Existing solutions with LDP cannot provide the strict epsilon LDP or require much external public knowledge. We propose a novel private trajectory data collection mechanism that satisfies for epsilon LDP. We model trajectory perturbation as a two-stage process, which first estimates discrete directions and then performs location perturbations. The proposed mechanism is further enhanced by adaptively restricting the trajectory region. To the best of our knowledge, our solution is the first to combine direction information with the perturbation of a trajectory and LDP. That's all. Thank you.